Okay, so now I will be discussing the elastic properties of the lung and the chest wall and the pressure-volume relationship. So when we're looking at altering the effectiveness and efficiency of ventilation, so the energy costs of ventilation, there's two main things that we think about. Firstly, we have elastic properties of lung and chest wall, which I'll go through now, and the resistance of the respiratory tree, which is important for determining flow. So how do we measure the elastic properties of the lung and the chest wall? So we can plot a pressure volume graph, which allows us to do this, and the way that we do it is we have the lung in a closed jar, and then we have the negative pressure gradient. We can create a negative pressure gradient here, and the lung is attached to a spirometer, which determines the volume, and a pressure gauge as well. And that's how we measure those two variables. Now, as we decrease the intrapleural pressure, we expand in the lungs, and remember that if we're at zero pressure, then the lung has an innate volume, so we don't start at zero. And as we decrease the intrapleural pressure, we expand in the lungs, and we're inflating it, so the volume increases like this. Now, when we deflate it, the curve is a little bit different. They both end and start at the same place. Now, a few things. So we can measure the static compliance of these curves by using dV over dP, change in volume over change in pressure. This shows us the static compliance, so the stretchiness of the lung when there's no airflow, and we take measurements at different points. So the more compliant the lung, there's a bigger volume change with a change in pressure, the stretchier your lung is, whereas with decreased compliance you have a stiffer lung. And there's decreased compliance as the lung has increased in volume, and as it decreases in volume it becomes more compliant. So there's also this phenomena called hysteresis, and hysteresis in general means that something going in one direction is not the same going in the other direction. So here, the lung volume at a given pressure, intrapleural pressure, during deflation is always higher than during inflation, so you can see that as it deflates, the static compliance is a lot lower. And we'll get onto why that is later. It's because of surface tension and something called surfactant. So let's look at lung compliance and factors affecting lung compliance. So remember, lung compliance is how stiff or how stretchy the lung is. So firstly, the volume of the lung, as we saw. So at a higher volume, the lung is less compliant, and at a medium volume, the lung is more compliant generally. So generally, with an increased volume, the lung is less compliant. And secondly, we've got the innate elastic properties of the lung. Thirdly, we have the lung size, and to account for this in different species, we use something called specific compliance. So specific lung compliance equals the actual compliance divided by the functional residual capacity. And we do this because we normalize the lung compliance according to size of the lungs. So it counts for site difference, and a decreased lung size, for example, a mouse will have a decreased compliance. And the specific compliance after you've accounted for lung size is about 0.08 centimeters of water for many mammals. Surface forces in alveoli are something that we will look at as well, which affect lung compliance. And also another thing which affects lung compliance is what part of the lung you're looking at. So there's regional lung compliance, and you might already imagine that the top of the lung is less compliant than the bottom of the lung, and that's because of gravity. So the top of the lung is sort of getting squashed by gravity, it's getting compressed, and it's harder to expand it, so it's stiffer, it's less compliant. And the area at the bottom of the lung is slightly more compliant because gravity is helping it pull down, so it inflates slightly easier. That's the theory behind it. So if we look at the pleural pressure versus lung volume graph, we've got breathing in, breathing out. So the bottom of the lung will have a slightly smaller negative intrapleural pressure than the top of the lung for any given size or percentage of lung volume. So it will be in this portion of the curve, which is more compliant, as you can see. And at the top of the lung, you'll have a more negative or greater pressure for a given percentage of lung volume. So it will be in this portion of the graph, the less compliant portion. Now, there's further evidence to show that the lung is more compliant at the bottom than the top. And this is if you get someone to breathe in xenon gas, so xenon 133 gas. And this is radioactive, so you can put a radiation camera in front of their thorax to detect where this gas is going. and you can detect an increased density of the gas, so more of the gas goes to the bottom of the lung and the top of the lung, and that's further evidence that it's more compliant there, so more of the gas that you breathe in goes there. As lung volume decreases towards residual volume, the intrapleural pressure becomes greater than the atmospheric pressure and compresses the base of the lung. So as the lung volume decreases, actually, the top of the lung ventilates better, so the intrapleural pressure at the apex is more favourable. So it just depends on where you are in this curve. Now, there's a lot of functional consequences of alterations in lung compliance, as you can probably imagine. So when we lose our lung compliance, the lung becomes stiffer, and this can occur because of fibrosis or scarring of the alveolar membrane. If someone breathes in carbon particles like coal miners, you can get something called black lung. If you breathe in asbestos particles, which are very dangerous, such as boilermakers, they're in danger of breathing in asbestos particles and getting asbestosis. And this is an occupation-related hazard, so on a death certificate, actually, if someone dies from this, then it has to be reported. Cellulose particles can also damage the lungs and decrease their compliance, so textile workers are in danger of this, and this is something called brown lung. Silica particles endanger gas workers, and silicosis is what they cause. So as a consequence, the lung becomes more stiff, it requires more work to maintain the normal alveolar ventilation, and increases the cost of breathing, so you have to inhale harder to breathe. Now, an increase in lung compliance is slightly different. It's usually caused by emphysema, so the lung is stretchier than normal, and the elastic properties of the lung change and are lost because of alveolar damage. So the alveoli might be burst or have lost some of their elastic properties. And people with increased lung compliance have no problem inflating their lung, but it's very difficult to exhale, so you can't breathe out because of the loss of the elastic recoil properties of the lung. Now, this graph shows the pressure-volume relationship of the lungs and the chest. So we've got the transmural pressure that we're familiar with, and then on the y-axis we've got percentage of vital capacity of that area of the body that we're looking at. So we can see that as the transmural pressure becomes more positive, both the chest wall and the lung, albeit starting at different places, but both of them increase in their vital capacity, they expand, and we can have a look at the combined effect of the lung and the chest wall. So we're really looking at functional residual capacity here. So if a normal person's functional residual capacity would be about here, so about 30 to 40% of their vital capacity. And this is where the transmural pressure of the lungs is positive, the chest wall is negative, and there's an equal and opposite opposing pressures from the lung and the chest wall. So the lung is tending to collapse inwards and the chest wall is tending to bound outwards. There's a negative intrapleural pressure that is stopping that from happening, and this is at the functional residual capacity. Now, if someone has lung problems and they decrease their functional residual capacity, so or they increase their functional residual capacity, then the lung compliance changes. So with decreased functional residual capacity, you have decreased lung compliance. The lung is more stiffer, and you have a negative pressure, so the lung is tending to collapse. If something makes your functional residual capacity increase, then the lung compliance will be increased as well. Now, the determinants of the characteristics of the chest wall and the lungs. So what determines chest wall compliance is dependent on the rigidity and the shape of the thoracic cage. Decreased compliance if it's deformed, for example in obesity, or in abdominal disorders, for example diaphragm elevation and skeletal muscle disorders. Lung compliance depends on the elastic characteristics of the lung and the surface tension generated by the air-liquid interface at the inner alveolar surface. We'll have a look at what this means later. Surface tension at the air-liquid interface is important because attractive forces between adjacent liquid molecules are greater than between the liquid and the air molecules above. So that's what maintains surface tension. Now, before we look at surface tension in a bit more detail, we need to know what Laplace's law is. So Laplace's law says that pressure equals 4 times tension over radius. And this is basically relevant because the liquid surface of the alveolus becomes as small as possible, condensing into a sphere, which is the 3D object which has a smallest surface area to volume ratio. So the pressure, as we said, is governed by Laplace's law. The pressure inside the spherical alveolus, and in this case the number here is 2 because the alveolus only has a single air-liquid interface, so in an alveolus the pressure equals 2 times the surface tension over the radius. We'll have a look at why that's relevant later. Now, von Neergaard's saline experiment, what this guy did was he took the lung of a cat and inflated it, then deflated it with air, and then repeated the same thing with saline. And these were something like the results he got. So this is this is pressure inside the lung, and as he increased the pressure, so breathing in, breathing out, the volume of air decreased and increased as normal. And with saline, you can see that there was a much higher compliance, so the lung inflated and deflated much faster, and you can see that there's hysteresis in both cases. So depriving the air-water interface with saline increased the compliance, and surface tension accounts for about 2/3 to 3/4 of the elastic recoil of the lungs. Now, surfactant is responsible for managing the surface tension. So workers studying edema foam from animals exposed to noxious gases found that tiny air bubbles in the foam were extremely stable because of decreased surface tension. Surface tension makes things less stable, so if you decrease your surface tension, then you make a 3D shape more stable, like a sphere. So some cells lining the alveoli secrete pulmonary surfactant, and this decreases the surface tension of the alveolar liquid lining. So that will tend to increase the lung compliance. And surfactant, the chemical, is actually called DPPC, or dipalmitoyl phosphatidyl choline, and that's related to its structure. So if we look at, so this is the endothelium of the alveoli, and then these are the type 2 alveolar cells. This is the liquid that's in contact with those cells, and then this is the liquid air interface, and this is just gas, so air is being exchanged here. And you can see many of these surfactant molecules lining the liquid air interface. And if we zoom in on one of these surfactant molecules, so this is gas and liquid, you can see that it has a hydrophobic part and a hydrophilic part. So this part is charged, has a phosphate, negatively charged choline as well, and a glycerol, and these two palmitate or chains of hydrocarbons are hydrophobic. So it's a bit like a detergent. It has a hydrophobic and hydrophilic end, or an emulsifier, if you know what that is. And the substrates used to produce this chemical, DPPC, are glucose, fatty acids, and choline. What is the role of surfactant? So as we know, it reduces the surface tension in the alveoli, which increases the compliance and decreases breathing work. And also, it allows alveoli of different sizes to exist. So Laplace's law again, if we've got a constant pressure of 50 dynes per centimetres, then we can see here that two alveoli with different sizes and no surfactant. So let's calculate the pressure in the larger alveolus. We've got pressure equals 2 times the surface tension with 50 dynes per centimetres over the radius equals 2000. And in the smaller one, we've got pressure equals 2 times 50 again, surface tension doesn't change, over 0.025, which is 4000. So there's a higher pressure in the smaller alveolus than in the larger one, so air is going to tend to flow from the smaller one to the larger one, and this one will collapse. Whereas if you have surfactant, then we can calculate this one, so nothing's changed here, the pressure's still 2000. But then if we've got surfactant, then that decreases the surface tension, so now it's around 25. And 2 times 25 over 0.025 is 2000, so we've got equal pressures, and the air will flow into both of these different sized alveoli. And the surface tension decrease amount, so this halved the surface tension, but the amount that it does that depends on the amount of surfactant per unit area. And at low lung volumes, smaller alveoli collapse. This is called atelectasis. And surfactant promotes small alveoli stability by decreasing surface tension in smaller alveoli. So it has these two main roles with respect to surface tension management. So how does it actually do this on a molecular level? So the molecules are aligned in an inner alveolar surface. We've got intermolecular forces. So there's intermolecular forces between the water, which are causing the surface tension and causing making the alveoli more likely to collapse. But these molecules are aligned, as you saw here. So they're aligned and they sort of decrease the attraction between the liquid molecules. So the lung can expand a bit more easily. So if we imagine the water is kind of like glue on a molecular level, then this these surfactant molecules are kind of making the glue a bit looser, if that makes sense. So they oppose the attractive forces between the water molecules. Now let's have a look at surface tension and why it causes hysteresis, as we saw before. So if we plot the surface tension against the relative percentage of area, we can see that there are changes as we breathe out and as we breathe in. So when we start here, so we've just taken a deep breath in, the surfactant molecules look something like this. They're spread out pretty evenly. And as we breathe out, the surface area and the volume of the lungs decreases, so these molecules get a bit more squashed together. And then as we breathe out more, they get smaller, and then they get all clumped up together like this. And as we saw before, the more surfactant molecules we have in a given area, the more compliant the lungs will be. So it's much easier to breathe in than to breathe out, basically. And as we breathe in, the lung expands, and then these surfactant molecules spread out again, so we have the highest compliance here and the lowest compliance here. So you can see as we breathe in, the compliance decreases and makes the lung stiffer, and that means that as we breathe out, the surfactant molecules are a bit more spread out, so the lung is stiffer and the compliance is decreased initially. So patients that have undergone abdominal or thoracic surgery often find that deep breathing is too painful because poor surfactant spreading causes atelectasis because of the increased surface tension. So their alveoli tend to collapse. Now the fetal lung has inadequate surfactant production, so you'll know from my cardiovascular lectures, hopefully, that the fetus doesn't really use the lungs, so the circulation bypasses the lungs, and that's because the surfactant production is inadequate until the fully mature lungs at around 85 to 90% of gestation. And this can cause infant respiratory distress syndrome, which tragically happens to a lot of premature babies. And this is often caused by impaired surfactant production. So the decreased compliance of their lungs increases the surface tension and causes laboured breathing and atelectasis and pulmonary edema. And another role of surfactant is likely that it keeps the alveoli dry. So it provides a barrier between the air-water interface and stops the water going into the actual alveoli and being breathed in and out. And it lowers the surface tension, so it reduces the tendency for the alveoli to collapse. And this lowers the interstitial pressure and pulls fluid from the capillaries, so it reduces the tendency to pull the fluid from the capillaries.